Let's take a look at example 14.3. Okay, we got some sort of crane and it's lifting this beam here. The force is applied directly up, and go ahead and use this as a free body diagram. We have the weight pointed straight down. So we have this force as a function of S, and it's given in meganewtons, but let's call that times 10 to the third newtons. When they give us the mass in megagrams, let's go ahead and call that times 10 to the third kilograms. They want us to find the speed of the beam after it's gone up 3 meters and the time to get up 3 meters. So the first things first, if this is a function of S, the force is a function of S, is it even lifting enough at S is equal to 0 to start moving? In other words, if we compare the force at S is equal to 0 by plugging in 0, how does that compare to mass times gravity of the beam? Or the weight, right? We get a force of 28 times 10 to the third newtons, and the weight ends up equaling 2.5 times 10 to the third times 9.81. Alright, this is bigger. So what does that mean? That means the instant the force is applied at S is equal to 0 at ground level, it doesn't have to be ground level, it's just where we're calling 0. The instant the force is applied, it's going to start going up. So now let's use principles of work and energy. So T1 plus the work done from 1 to 2 is equal to T2. This is initially 0. That's our kinetic energy, and we don't have any. Kinetic energy requires a velocity, and the velocity was from rest, and it started so that makes the kinetic energy 0. Open up some brackets here, and let's put our different forms of work. Well, we know we're going to have the lifting force acting at some distance, so since it's a function of S, let's integrate that force. The force is 28 plus 3s squared, and let's integrate that from 0 to S. We can plug in 3 meters later. We're also going to have a 2.5 times 10 to the third times 9.81 going down times S. Don't forget that S right there. This is very commonly forgot. So why do we not have to integrate this one? Well, this force is constant. This force is a function, F is a function of position, so we have to integrate it. And this is all going to equal some 1/2 mv final squared, or some T2, kinetic energy. We are looking for the final velocity, and all we have to do is integrate, substitute. We can get a function of S. V is equal to 2.78s plus 0.8s to the third, and then we take the square root of that whole thing, and then we can plug in any S. They're concerned about S is equal to 3 meters, and plugging that in, we can get 5.47 meters per second. Alright, that's how fast it is going. Notice we didn't deal with acceleration anywhere. We had a force, but instead of dealing with the acceleration caused by the force, we looked at the work. Same thing with our energy methods. We're going to be dealing with forces, velocities, and displacements mainly. Okay, the second part of the problem wants the time to s is equal to 3 meters. This is not so intuitive necessarily, but our velocity we just got ended up as a function of position. Or displacement. Alright, that's why I don't always recommend substituting your limit right away. We still like this as a function s because we're going to use that. So let's use the definition that the velocity is equal to ds dt, the time derivative of the position, and the velocity was given right here as 2.78 s plus 0.8 s to the third, all raised to the 1/2 power. Now I can rearrange so I get dt by itself, and my s is all on the other side. And we're going to integrate from 0 to t. And then on this side, we're going to have ds on top and the function of s on bottom, 2.78s plus 0.8s to the third, all square rooted. Okay, we can integrate that now from 0 to t. It started at time is equal to 0. And we can integrate from s is equal to 0 to s is equal to 3. This gives us our time as 1.79 seconds. Also, check out the book. Most of these problems have a second solution that can be used with equations of motion. In this case, they use VdV is equal to AdS. Remember that definition. And you sum the forces, Newton's second law, to get your equation of motion. I'm not going to do the full problem, but what's your force? You have the 28 plus 3s squared. This is all times 10 to the third. We also have a minus mg pointed down, and that's going to be equal to the mass times the acceleration. Now this acceleration will come out as a function of s and can go in there. So we could still find the velocity. Go ahead and try it out. Make sure you can do it both ways. This unit, we're going to focus on energy methods and work methods though.